Okay, hello. I would like to present my paper, Tag and Correct High Precision Post-Editing Approach to ASR Errors Correction. Okay.
We can see you and we can check that you are correct.
Okay. I'll start with a short introduction and motivation for my work. Then I will introduce data I worked with. Then I will present the proposed method, results, and I will conclude with conclusions. So another title page, that's the title page of my paper, and I'm showing it to also to show some context of this research. So this research is part of my applied or industrial PhD. I'm doing in collaboration between Adam Mickiewicz University in Poznań and Samsung Research Poland. So this is important to understand the context, and that this research has to be applied by my employer, and it's the industrial context is important here. Okay, so as you probably know, Samsung produces a lot of devices like mobile phones or TVs, which use speech recognition. And well, this problem of automatic speech recognition may seem a solved problem. State-of-the-art models are reported to outperform human annotators, and levels of word recognition rates are as high as 27 or 28%. So there's not much left to correct. Yet this is only one side of the story, and production reality doesn't look so rosy, because these state-of-the-art results are reported on well-known data sets, recorded in well-known conditions, and the models are tailored to achieve as good results as possible on these restricted corpora. But in real day usage, when we have general purpose automatic speech recognition system, and we use it in specific domains, in specific conditions, the model can be still imperfect. And the conditions may change. Let's say that we created a model in 2019, then come COVID, people start wearing face masks, and people start talking about COVID a lot, and our model, our ASR system can misrecognize a lot of words, and we have to adapt to these changes. So we could, of course, adapt a whole ASR model by retraining it, or retrain parts of it, like language model or acoustic model, and of course it's doable, but sometimes it's not possible to do it. For example, because let's assume that we are a small company and we use some cloud-based product, and we just cannot modify it. And even if we are not, if we have our own system and we can retrain it, well, it's costly. It costs a lot of money, and it also costs a lot of time. Maybe we want to adapt faster to these changes. And even if we can, and even if cost is not now the problem, and even if we can retrain the ASR model in quite fast, it still may be good to have another model which will improve the results even further. So what do we propose? We propose to correct errors of automatic speech recognition system at the post-processing stage, which means that in a production setting, when the system is ready and is used, user says something to a device, sound is sent to automatic speech recognition system, it returns recognized text, an ASR hypothesis or response. And this response is processed by the error correction model, which returns corrected text to a user. So quite simple scenario. What's quite important here is to stress that this error correction system works on text only. Yeah, so it just gets single sentence from ASR, one best hypothesis from ASR system. And how could we train this kind of system? So we have to collect some speech corpus, which is collected by recording some sentences, then annotating them by humans, which gives us a speech corpus, so corpus of parallel recordings and their annotations. And then we can use the speech corpus to feed these recordings to automatic speech recognition model, which returns recognition results. We pair them with reference sentences from the corpus, and on these pairs of correct and possibly incorrect sentences, we can train an error correction model. So that's the problem I want to solve. And before I will tell how I tried to solve it, I'll describe the data I used. So the data, to prepare the data, we're starting from the speech corpus. As shown on the previous slide, we feed it to automatic speech recognition system. We get these pairs of ASR hypotheses and references. We normalize them, and we get a correction corpus of parallel corpus of incorrect and correct versions of sentences. And we did it for 3 languages: German, Spanish, and French. Domain of the corpora used was virtual assistant. So these were comments spoken by people to a virtual assistant. They were from 2 sources. They were either recorded in a studio or from usage data, so from different conditions, wherever users use their devices. And these recordings were processed by state-of-the-art end-to-end ASR models, separate model for each language. Dataset sizes looks like this. So they range from 7,000 sentences up to about 17,000 sentences. And these sentences are on average not too long, about 3 to 4 words. Well, that's not surprising. Most of the comments are like turn on a torch or volume down, etc. But they may be also longer. And what's important here is the last column, ASR word recognition rate. Word recognition rate is a metric used in speech recognition, which tells us, well, let's say a percentage of words which are correctly recognized in a sentence. So this is averaged over whole corpus. Well, the results differ here per language, and it's not necessarily because some models are much worse, but the corpora they are evaluated on can be much more difficult, like recorded in different conditions and so on. And we wanted to have such a diverse results to see how the correction model performs on when it has more errors to learn on, and how it performs when it doesn't have too much errors to learn on. And we split the data sets in proportion 8 to 1 to 1 between train, development, and test subsets. Okay, and so what did we do with this data? So first, I would like to say how most of related works, and how different solutions work. So mostly they are end-to-end, sequence-to-sequence models inspired by translation models. So they are trained to, let's say, translate incorrect sentences into correct ones. And it may seem a good idea because we were good at translation, but it requires a large speech corpora. As we know, translation models require a lot of data. And in case of translation data, this data is not so hard to acquire. In case of speech, you have to record every sentence, and we just don't have as big speech corpora as we have parallel corpora for translation. So some authors generate additional data with text-to-speech, which requires us to have a good TTS system. And what's more, these systems can sometimes introduce new errors, some hallucinations, and they are not so easy to control as our system. I will explain why in a minute. So what I propose is to tackle problem in this way. We have to first align ASR hypothesis, so this possibly incorrect sentence with the correct one. When we do the alignment, we can see which words were altered, which parts of the sentence are different. And using some predefined rules, we can extract edit operations from the alignment. These edit operations tells us how to transpose the incorrect words into correct ones. I will show an example in a minute. And this way we create a corpus of the ASR hypothesis tagged with this edit operation, operations. And on this corpus, we can train some Stagger model, which is then used on production to tag incoming ASR hypothesis. When we have this hypothesis tagged with these operation labels, we can apply them to fix the errors. So if it wasn't clear from the description, I hope it will become after seeing this this image. So here we have this parallel corpus of hypotheses, which is possibly incorrect, and reference, so correct sentences. We align them. Here the example is simple. There is no problem with the alignment. We can see that words 2 and 3 are correct, but the first one is changed. Yeah, so from the alignment, we see that we have to do something with the first word. And then we compare these words which are different. And we have a predefined set of these edit operations, and we look for edit operation which is able to transpose the incorrect word into correct one. In this case, it would be operation append s, which appends one letter s to the end of the word which is tagged with this operation. And after applying this operation, this incorrect sentence would be turned into correct one. Yeah, and how this model is used on runtime. Well, ASR model returns some hypothesis. Then we have the Stagger model trained, which tags every word in the hypothesis with some tag. So here, first word is tagged with append s, and others are tagged with none, so an empty operation. And then there's a model called editor, which applies these edit operations, or does not apply them. I mean, we can filter some of these operations if we want. and it returns a corrected hypothesis. In this case, cats are cute. Okay, another example is not needed because we are running out of time. And here are examples of these edit operations. So these are just a few, but most popular ones. So, for example, operation deal or delete, it just deletes a token. Yeah. Append S, we've already seen it. Of course, this S can be changed for any other character depending what was seen in the training set. We can have a lot of different operations like append S, append A, and etc. We can, of course, add prefix, so prepend some characters to the beginning of a word, delete prefix or suffix of a given length. We can join two tokens which are next to one another. We can finally we can just replace a whole word with another word. Yes. Okay. And so now let's go to the taggers. Yeah, we know that we have a corpus of these ASR hypotheses tagged with these edit operations. So some words will have these edit operation labels assigned to them, and now we have to train a tagger model which will learn how to assign these operations on in a test or production phase. Yeah? So I tried two types of taggers. I called them bird tagger and flare tagger. So first, the bird tagger. It's a bird with a single layer added at the output, token classification layer, and whole network is then fine-tuned for this specific tagging task. As the base models, I used national birds, so dbird for German, camembert for French, and betel-free for Spanish. Yes, so that's one tagger model, and the other I tried as I called it flare tagger because it uses flare natural language processing library or framework, and it can be seen as an extension of the previous tagger because first it used bird layers, just the ones described here, and then it has added contextual string embeddings, so something specific to flare. Then LSTM layer and CRF layer, so conditional random fields layer at the end. So much more, a little bit more complicated model than the previous one. And now I would like to present results. Results for these two taggers for different languages. So how do we read these results? First, we have word recognition rate for ASR alone, so the base result we're starting from. And then we have word recognition rate after applying the correction model. Of course, these are results on a test set. I have also computed word recognition rate gain, so that's just an absolute difference between the ASR result and result after correction, and relative word error reduction rate, so how the percentage of errors which we're able to correct. Yeah, this result, this relative reduction allows us to compare results for different base results here. So we can compare results for an ASR which had only 78 word recognition rate and 93, because this absolute numbers don't allow us to do it. Yeah. Okay. So what we can see here is that there's no much difference between these two models in terms of the results. Well, FLAIR is slightly better for Spanish and for French, which were more difficult because there was less errors to correct. And if we compare these results, this relative word rate reduction with other research, it's on par with them. I mean, other models achieve similar levels, about 20 to up to 30% of this relative words error rate reduction. But it's hard to compare them because we are using different corpora. So that's one of my future tasks which I want to do. So to compare this model on a well-known corpora with other models. Yes. Okay, what to add here? Okay, maybe I'll just go to conclusions because we are out of time. So as I said, the results are comparable to state-of-the-art results, but it's hard to compare if we are not comparing on the same data sets. But what's the big advantage over other models is that they don't require big training sets. These sequence-to-sequence models, for example, they worked on data sets of sizes like millions of sentences, and we had only about 10,000. And what's maybe even more important is that this model is highly adjustable. So in case of this end-to-end sequence-to-sequence translation models, we can manipulate the input data, and then we have that. No, we can also manipulate some meta parameters, hyperparameters of model training, and we get some results. But then we just get output sentence, and we cannot do much about it. And it can, as I said, it can introduce some new errors, some hallucinations. And of course, it can also happen in case of our model, yes, because its precision is not perfect, and it will sometimes tag correct words with some edit operations, so it will change correct words into incorrect ones. But we can fine-tune it by in many ways. Yeah? So when Stagger returns an edit operation, it also returns a score. So we can, for example, set some threshold for the score and say that we just don't apply the edit operations with score lower than some threshold. Or we can filter out some set of edit operations if we just if we, for example, see that the model is not good enough in predicting these specific edit operations. We can also adjust the set of edit operations on training time. Yeah, so we can, for example, train only model for joining words two tokens, yeah, with some connectors, or we can train a model which only restores capitalization, for example, yeah, and so on. Yes, so this way we can easily correct mistakes of the model and control how it behaves. Yeah, and as I said, as a future work to do here, I would like to compare my model to similar model proposed by Google, which is called Laser Stagger. Their approach is very similar. but they used it on different tasks, on grammar correction, not on correction of ASR results. So I would like to use my model on their data set, so this grammar correction data set, and to compare them, and also train their model on our data sets to also be able to compare which one is better. Their model is different. It uses much smaller set of edit operations, and it's I would say that it's not able to generalize so well as our model because of that. Also, some detailed error analysis would be useful, and after doing this error analysis, the set of edit operations would be refined, so we can express these transformations from the incorrect to correct version using different edit operations, so they can be optimized. Okay, that's all. Thank you for your attention, and I'm waiting for questions.
Okay. The question is, you use French, Spanish, and German. They are quite different, and German is quite tough for NLP. Why not Italian? Because it's quite close. The result could be much better. And the second question, maybe it's connected. You use French, German, and Spanish, but your example was in English. Does it mean that you are doing transfer learning? Or?
No. Okay, so the example was in English just for the sake of simplicity and for readers to be able to understand it more easily. Yeah, I don't do transfer learning, and why we didn't use Italian, well, I had to restrict the set of languages to because of time constraints for the experiments and so on. Yeah, but it would be a good idea to include more languages. So.
Yes, and it works to think because German is crazy language. They are can split and join whatever they would like to join. Yes, so it's crazy. But in French and Spanish, you have quite, okay, maybe in French not exactly, but they quite rigid grammar and rules and whatever. The same in the Italian language and Spanish. They are quite close. So, for example, if you know French, you can more or less understand Spanish and Italian. So it could be quite useful for result.
Yeah. But at the same time, having very different languages brings better understanding how good the approach is.
And I think that train models, and so you can go to the different language.
For instance, I think that for a variety of reasons that I will not specify, Korean would be a good language to add to the mix, isn't it? But I have a different question. I have a question about the size of the model that you have, meaning is it very big? The final trained model, okay? Can you run it from a cell phone?
I didn't try. It was just research project, and if we would like to deploy it on mobile phones, I think it would be possible, but we'll have to compress the model with something.
Well, this is, you see, it's one thing to have a model that is running on a supercomputer, but for it to be useful, you don't have to really try it on the phone, but it just makes some assessment. I think that in your research it would be good to take, and you have some Samsung there, so take top of the line Samsung, upload the model into it, and see how inefficiently it works. Not necessarily because all the compressions and so on, it's a different line of research that you may not have time to do during your doctoral studies. But just to be able to answer somebody like me and say, yeah, I mean, of course, on the old model of Xiaomi Redmi Note 7, it will not run, but on the top of the line Apple or Samsung, we tried it, and it sort of kind of works. It's a good linking to the practice. Okay?
Yeah, that's right. Thank you. Can also tell that in a previous research, I tried conditional random fields models, and they will be better suited for this application. But in preliminary results, well, these models were just much better, and so I decided to try
this is okay. It's just, you know, having this perspective within your doctoral dissertation, having like little section on applicability for currently top of the line phones would be useful, because it is to be used in this context. Yes, in some at least way.
Congratulations on your presentation. You mentioned that your approach doesn't need too much data when training. My question is, does your approach support all the vocabulary words of the language, or only the words of the dataset?
Yeah, so well, it supports not only the vocabulary found in training data. Let's say that the model learns on the example from training set that it has to append a letter S to the words which are followed by a word R, yeah, like cats are cute, like in this example, yeah. So it could generalize this rule and append this letter S to the words which were not seen in the training set, just basing on the context on the next on this word R, which is after the current word, yeah. So it should work also for words which weren't in the training data. I hope it answers your question.
Right. Okay, thank you very much.